Good morning or afternoon. I'm Ryan Honeyegger, and today I'm going to talk a little bit about C++. The focus for this lecture is different than the earlier talks that showed code on screen, because those talks focused more about the JEDI applications, but this talk is going to focus more on the essential features of C++ and some best practices. So let's just start with a fundamental question. Why do we care about C++? And for that, the answer is simple. We want a programming language that can produce very fast code that also has support for the expressive templates and patterns that we're using inside of OOPS. We want to have compile time produced interfaces between the core of JEDI and our models, and we want this for performance. And really, performing languages are not at all equal. They have different benefits and drawbacks, and we looked into it. OOPS was barely even possible with Fortran, and moreover, Fortran doesn't have much new development these days. There really aren't many libraries or tools that we could build on, so we would have to have developed a lot in-house. Python could have provided some of these benefits, but it wasn't likely that we could have extracted enough performance from it. So we have done some surveys of Academy participants, and attendees of last year's February Academy indicated that they were mostly unfamiliar with C++, and only about 60% of the audience had any familiarity with object-oriented programming. So this talk will be more introductory or explanatory, and the goal is to make you comfortable with reading the structure of the language. So that being said, there really is no substitute for practice. I have some links peppered throughout this presentation, so you can download the presentation from our Academy webpage and just click on the links. And for those in need of a good tutorial, then I recommend c++.com. If that doesn't work, then geeks4geeks.org is also quite decent. And Google is also really your friend here. It's important to mention that C++ has a very long development history and that some techniques and practices have proven to be better than others. So before you get into bad habits, but after you become a little bit more familiar, I recommend reading the C++ core guidelines. And those were created by the creator of C++. Also, half of C++'s greatest strength is in the core language, but the other half is in its third-party libraries. So those are what make the language do cool things, and I would really rather not have people reinvent the wheel. So for those, I would suggest that people take a look at Eigen and Boost. So to really talk about why we want C++, we need to revisit some ancient history. So in the 1900s, actually 1904, the first vacuum tubes were invented, and then later on we had transistors, and then we started making calculators with these devices. So these calculators were really simple, and frequently they lacked any type of disk or storage or really any memory, and they had only the most basic I/O, basically just a keypad. But still, these calculators powered some of the very first attempts at weather modeling and powered our ability to go to the moon with NASA missions and the like. And originally, you could write a set of instructions manually that the machine would work on, but you would have to write these instructions one by one, usually through a series of switches. And this grew really tedious to code. So the first basic assemblers were invented that replayed macros and turned them into machine language instructions. And this way you could do the same programming task a whole lot faster. But then later on, people got tired of writing these macros and having to know all the intrinsic differences of each computing device, like its instruction set and its endianness and its register arrangement. So they started making the first programming languages. And Fortran was one of these early ones, and it had rapid development up through the 90s. And on a parallel track, we created C to act as a systems language. So that is one that retained the ability to manipulate the lower levels of a system while still providing enough high-level features to be usable. So operating systems have commonly been written in C, and it still powers the Linux kernels and the core of Microsoft Windows. It is different from Fortran in that it needs to use these low-level concepts like using memory pointers and supporting many semantics for transferring data between functions. But since so much was invested in developing these features for the language, they still are used extensively, and C++ picked up on a few of them, and I'll mention some in later slides. Anyways, I think it's good to start with the simplest programming exercise imaginable, and that is the Hello World program. And surprisingly, this program uses many of the core features of C++, but people new to the language don't realize what they are using and how it all works together. So I'm going to introduce a few new concepts one by one and show where they're relevant either to here or perhaps to some contrived examples or to different parts of JEDI. So first, though, it does help to give everyone an idea of what a C++ style program or even really a C++ style function looks like. So any program in C++ is built up from a series of functions like this one, and you can view the program as a series of functions that call other functions. So you begin with a function called main, and then you just call other functions, and this extends until a program finishes execution. So here's how you read just the typical function. So hopefully you can see my mouse, but every function in C++ starts with the declaration somewhere. So when we declare a function, you've got the name of the function, so in this case, custom function, and then you've got some parentheses. And then inside the parentheses, you have parameters that you pass into the function when you call it. So each of these parameters needs a type, which might be an integer or a float or a double. And optionally, the parameter also needs a name in case you actually want to use it later. So unlike in Fortran, C and C++ by default use what's called pass-by-value semantics, where input data are always copied. So when you're dealing with small parameters, say like a single number, that doesn't really matter. But if you're trying to pass something very complicated or large, you don't always want to do that. So if you see an asterisk or an ampersand anywhere, we're instead passing by pointer or passing by reference, in which case we're passing the wrong memory location and a copy doesn't get made. So for a function, you have its declaration, and then this function also has a return type, just like a Fortran function. However, C++ doesn't have Fortran-like procedures. Instead, everything is a function, and if a function returns nothing, then it gets a special return type called type void. So now that you've declared a function, then you use braces to denote the function body, and braces are also used to denote different levels of scope. So for example, this return value parameter in the function is only available inside the function itself. You can't directly access it from outside of the function. We might have another parameter or a variable, say I, that is also not accessible outside of the function. If we would declare it inside this level of scope, then the moment you left this level of braces, it would no longer be accessible. So speaking of parameters or variables, variables all have a specific type that you declare. C++ is a strongly typed language. We don't make implicit assumptions about what type of data a variable stores based on, say, its first letter, like in Fortran, or say just based on arbitrary constraints like in Python. So you have many different built-in types, again, like integers and floats and doubles. But unlike in Fortran, you also have unsigned data types. So you can have an unsigned integer. One other note, if a variable gets declared constant, then it can be initialized to some value, or maybe you can pass in a value initially, but then that value can no longer be changed. So that's basically what a function looks like. So in C, no two functions could ever have the same name. And this was related to how C translates function names into a low-level representation that the operating system could understand. And name conflicts caused many headaches. Several different programs implemented functions called read and write, and you could only ever have one of those. But then what if some other library wanted to have a function named read or write? What you would have is a name conflict, and your program wouldn't compile, and you'd have a massive headache. So C++ addresses this by adding in the concept of namespaces, which basically make logical groups of functions and variables. So a namespace lets you create a group, and really you can have names that are the same for a function or a variable that don't conflict. So in this case, we declare a namespace called oops and a namespace called Yoda. They both have got functions called do something, and they both have integers called some number. You can refer to them using this type of syntax. So oops, and then 2 colons do something, or Yoda, 2 colons do something. And again, these functions are distinct, so they don't conflict at all. And then what if you don't want to always type in a namespace's name? Then there's a convenience syntax for that called the using directive. And basically this just assumes in case you have some arbitrary name, check first in oops, and then if you can't find it in oops, then ask or have the compiler prompt for the user to be more specific. So now that we know what functions look like and how they're arranged, let me just also introduce some of C++'s more powerful features like classes and templates. So I'll start with objects and classes first. C introduced structures as a way to encapsulate groups of related data together. So think of a data record as opposed to having a separate array for every single variable that you've got in your model. When we do this encapsulation, you generally find that you want to add in convenience functions for manipulating each one of these records. So for example, you might want to initialize a new record, you might want to free it or deallocate it, you might want to append to it. And when you do this encapsulation, you generally find that you want to move towards the first step down the road towards object-oriented programming. So in C++ terms, what is an object? It's an instance of a class or the working entity of a class. And that begs the question, well, what is a class? And it's a template or blueprint about the capabilities of what an object can do. So here's a very simple example inside C++. And this declares a class, basically a type called a rectangle. And there's an object or an instance of this class called rect. So rect has access to all the different methods and the data that a rectangle will provide. So it's just a particular instance of this definition. So the class has 4 members. It's got width, height, set values, and area. And in this case, we have bound in functions and variables together. So we're encapsulating some data. So there are actually 4 general concepts that tie a class together, and I'm going to go through each one. So first, again, encapsulation. We stick the functions that we work with inside the class to avoid having to read too much when programming. So tie the functions with the data that they actually work with. Then we've got inheritance. So think of the idea of like rectangles and squares. A square is a type of rectangle. So coding-wise, you should be able to treat a square the same way that you treat a rectangle. Then we've got abstraction. You should always give a consistent interface to end users, and you don't let them muck about with object internals or internal data so that they can screw things up. They should go through a well-defined interface when they want to make a change. Then we also have polymorphism. Again, use the same interface, but perhaps use it to operate on different types of objects. So I mentioned squares and rectangles before. They should look very similar. So just to elaborate, here's an example of encapsulation and abstraction. So we have a class of rectangles, and by default, inside this class, all of the data members are private, which means that an external consumer can't access or modify the member variable directly. We don't want end users to take our objects and put them into inconsistent states when they just start modifying our objects directly. So instead, we set this up so that consumers have to go through the set values function to set width and height. And then we also have other public functions that anybody can access called, say, area and perimeter that work off of these internal objects. So again, with encapsulation, these area and perimeter functions are bound to the class itself. We don't have a separate function saying perimeter, which takes an object called rectangle. The second major concept of classes is inheritance. So in this case, we have rectangles and squares again. A square is a specialization of a rectangle. So if you see any type of syntax looking like this in the class definition, you have a square and it inherits from a rectangle. In this case, that means that a square has access to all the same functions that a rectangle provides. A square could also introduce some new functions, but we don't really need them in this example. So a square implicitly has an area function and a perimeter function because we've already defined these in the rectangle. The third concept is polymorphism and overloading. And the first example for this is function overloading. I mentioned this briefly before. So you can have multiple functions in C++ that have the same name, but with different function arguments. So you can have different function signatures. Here's how C does it. You would have to have a separate name. So say that you wanted to take the power of a number, say like raise an integer to the 2.1st power. You would have a separate name for taking the power of a double. You would have a different function name for taking the power of a float, and so on. So here's an example of the plethora of names that you have when you're trying to do math in C. So this is a very, very incomplete list. But to read this table, you think of the math that you're trying to do on the left, and then you go across the columns depending on which data type you're using. So just to take an absolute value, you had a separate function name for a float, for a double, a long double, or for a complex float, double, long double. And then this really went further to where you could have a separate name for every type of integer that you had and every type of long integer that you had, and so on. And here's how we do this in C++. So we are importing this function from one of our headers that's provided by the C++ standard template library. I'll describe that in a bit, but the C++ library provides a function called power. And basically, the takeaway is that this function is overloadable, so it can take different types. So you can pass in a double or a float, same name, no problem anymore. Now, we can overload more than just functions. We can overload entire classes too. So take, for example, just the idea of having a point. So what's a point is just a set of coordinates. In this case, a two-dimensional point has usually an x coordinate and a y coordinate, but it doesn't always have to have those. So you can have Cartesian points, which do have x and y, but you can also have polar points. So a polar point, instead of using x and y, is expressed in terms of a distance from an origin or a radius and an angle. So in this case, we can overload the functions, and we can actually overload a class. So we can have a class called Cartesian point. We can make an instance of it, and we can call x and y, and then we just return these basic values. But then if we declare polar point class, we also can just call the functions x and y, and you still have implicit math that goes on that converts the polar coordinates to your x and y coordinates. So we can extend this a little bit further. And the third really cool thing that you can do is that you can combine function overloading and class overloading, and you can overload operators inside of a class. And what this lets us do is it lets us do symbolic math on different types of objects, even say arrays and other containers. We can also use these operators in things like sorting. And with sorting, we can use, say, the less than operator to establish some form of order. Really, the exact algorithm is immaterial, but basically, any type of sort uses some form of less than compression or comparison. So in this example, we have a complex number. It has a real part and an imaginary part. Now, off in C space, to write a complex number, you would have to use specialty functions to add two complex numbers, to divide two complex numbers, and so on. In C++, because we can overload this operator, we can define addition of complex numbers, which produces another complex object. So we can define our complex numbers, and then we can just write, okay, Z or C3 in this case equals the sum of the first two. And then we're really translating a whole bunch of programming concepts into something that is very user-friendly or obvious. One final note about classes and objects, and that is that we have objects that contain functions and they contain data. And because we have objects, we also can implement what's called an object lifecycle. So when an object gets first made, it might store some data, and we have to allocate space to store this data. And then we can initialize this data to sensible values. And this gets accomplished inside of what's called a constructor. This constructor gets run every time we create a new object. Sometimes there are many different ways to make an object, in which case we might have multiple entry points or multiple constructors. But generally, what we want to do is we want to produce objects that are entirely initialized or ready for immediate use. As soon as you create a new object, you want to be able to use it. You don't want it to be in some half-initialized, unusable state. Conversely, when an object is done being used, like when it goes out of scope in a function, then it gets destroyed. So a destructor will free any resources that an object has acquired, and this provides a safe cleanup of resources that it owns or manages. So here are some examples of both. For this rectangle class again, this first function is the constructor. You have to pass in a width and a height for the rectangle to make sense. So you're required to provide those when you make the new rectangle object. And then it initializes the parameters to those values that you pass. Then once the rectangle leaves scope, say once you end your function, then the destructor would run. In this case, the destructor is very implicit or it's very obvious. It doesn't have to do anything because an integer is something very fundamental in C++, and the compiler understands how to just drop that data immediately. If you're dealing with something more complicated like a pointer or a very complicated object or a resource handle, then the destructor might have to actually do some logic. So now that we've got classes out of the way, I'm going to outline templates, and really there have been entire books written on the subject and how to use them. So I'm not going to go into the details for the interest of time. I will show you how some of them do get used in day-to-day tasks, however. So a template is a very simple and a very powerful tool in C++. And the idea is to save you a bunch of work by passing off this work to the compiler. So I talked about function overloading before, and say that you want to have a function that just computes the maximum value of two numbers. Now, with overloading, what a person would do is you would produce a separate function for an integer with all integer types, and you will make a second function if you wanted to take the maximum value of two characters. Then you would write another function if you wanted to take the max value of two doubles, and so on. So what a template does is you write it this way. So you declare that you're writing a template, and then you can pass in a virtual type, in this case t, and then you give a skeleton definition of your function. So instead of having an explicit integer, you use that type t. And then when the compiler goes through your source code and it realizes that you're trying to use a template, it automatically generates the appropriate definition of the function. So if you want to call the integer version of this template, the compiler writes this code for you and produces the integer definition. If you feed in a character, the compiler produces the character. And we really use this all over the place in OOPS and in UFO. So there are some template details that are interesting. You can make templates out of functions. You can also make templates out of entire classes and also out of variables. So in this first case, for example, you can have a constant such as pi, which is transcendental, and you don't want to have to redefine this constant constantly when you're using it with different types. So you can refer to pi as a float or pi as a double or pi as an integer. Then you also can, again, have a template class. So you might have a class which has an internal data member of an indeterminate type. And then there's that function example that I just went through. You can also have more than one template parameter. So you can have infinitely many template parameters, actually. So you can have a type T, a type U. Really, the spelling is arbitrary, but then you can use this inside of your functions. Third, you can nest templates inside of other templates. You can have a template class that has a template function, for example. Another takeaway of templates is that you can specialize templates so that you can have custom logic that runs for different types. And we use this a lot inside of the Yoda component of JEDI. What this means is that you can override the default definition depending on the parameters that you're using. So here's an example that just checks whether template's parameter is of type void or not. And really the concept matters. You can just as easily consider a situation where you want to do some branch of logic if a user passes in a bunch of integers versus if the user passes in a bunch of strings. And this matters particularly when people are manipulating dates and times and data in different ways. So in this case, if we're calling the isVoid character template, then this would give us a false. If we're calling isVoid value for a void template, then that comes out as true. So if you would run this example on your console, you get 0 and then 1. So I mentioned templates also because C the language has a standard library, but C++ has a standard template library. So this standard template library is built into every C++ compiler, and you've always got it available, which is really convenient. It's a large library, and the majority of functions in the classes inside are built off of templates in some way or another. So you can find containers of objects implemented with templates. So this includes sets, vectors, and maps. And I don't have enough time to really go into these, but these are different standard methods of storing your data. So with a vector, that's just storing a sequence of data that you have. With a map, think of it as a dictionary where you can look off of some key and then you can look up some value. For a set, that's just a set of numbers. So those are all implemented with templates. You can have a vector of integers versus a vector of strings versus a vector of some other custom object. You also have algorithms that are template-based, such as sorting algorithms. You have file and console input-output that is also template-based. You can write out floating point numbers, and you can also write out doubles without adding on special boilerplate code, and so on. Even strings are templated because you can have different types of strings. So you can have Unicode strings versus regular strings, or strings with different character widths or different character sets. So if you do want to explore further, I recommend the links in this slide. Every part of the standard template library is very well documented, especially on these websites. And there are even examples and usage examples for every class and every function inside of every class. So you can know how to use all these different objects. And really, the standard template library is very rich. So now that you've been exposed to some of the C++ details, let me just revisit that initial Hello World program that I showed many, many slides ago, and we can just break it down piece by piece. So first, we have an include definition, and we're going to import some functions related to text output from the standard template library. In this case, we're going to import this function called cout. I briefly mentioned that we're using namespaces, and we have using namespace standard up here. So cout can just be referred to as cout instead of standard cout. We've defined an entry point for our function, and that's called main. And you now can see how these functions are defined and what the rough layout is. And then when we're actually writing out some of our data to our console, we're using operator overloading, and we're using some template magic to print out character strings, integers, and floating point numbers to the user's console. Furthermore, this cout object is actually a class or an instance of a class. Finally, the function is returning a value of 0, indicating that the program has executed without error, and then it just returns your control to your regular console. So now you see the whole program. Now, I know that I've dumped a lot of information, and C++ is very big, so to close, I'm just going to mention a few best practices that help to keep you from pulling out your hair in exhaustion. So this isn't an exhaustive list, but merely what we see frequently when we're reviewing JEDI code. And you should really keep these in mind whenever you write any computer code, not just code for JEDI. So the first idea here is you should automatically assume that somebody else is going to get confused when they're reading your code. So please make it simple for them whenever possible. So here's an elaboration of that idea, and this is defensive programming. Say that somebody ever implements a function called change speed. This is very confusing because of several reasons, actually. First, what does the parameter mean? Are we changing speed to an absolute value? Like, are we changing a car speed to exactly 10 miles an hour? Or is this an increment or a delta? Are we increasing by 10 miles an hour? Second, we don't even have units here. So what are we changing the speed to? 2.3 miles an hour, 2.3 kilometers an hour, or what? So again, be very explicit either through the use of comments or through the use of these classes that we've provided. Sometimes it's very nice if you can write something in terms of meters and seconds. We could accept a plain unitless number, but that gets error prone. If we want to express both an absolute speed and a difference in speed, then we can define separate classes and we can use overloading, but then that makes it very easy for a user to not make mistakes. There's a few corollaries to this too. So first, you should always try and keep your function simple. So Don't have a function that contains dozens or hundreds of variables that spread up along 20 pages. You should really break up any large function into small, easily testable components that are no more than, say, 1 to 2 pages on your screen. Once you go past that point, nobody can keep track of it. Similarly, you should break up large pull requests or contributions into JEDI or another system into some very small, manageable fragments. No one wants to have to read 70 files touching 10,000 lines of code. We want to do agile development, so write your changes incrementally. Third, again, you can use comments, and you should really document everything that you write, because this helps everyone to understand the meaning of what you wrote. And here's an example of documentation that we've got inside of Yoda. And the format of this documentation is in Doxygen format. Doxygen is a program that reads in these special comments with little tags like brief and details and author, and it produces websites and PDF manuals that we then distribute with JEDI. We have a link to the Doxygen documentation for all of our JEDI products on our Read the Docs webpage. We use it a lot in JEDI, and you should really learn about the documentation system. I'm coming to the end. So finally, when we're trying to build new code, by default, leave compiler warnings turned on. We do this in JEDI automatically for you. So the compiler knows better C++ than you do, and it knows better C++ than I do, or really anybody else, and it warns about potential mistakes. Sometimes you write something that looks vaguely good but has subtle problems. One of the development ideas is that we try and not introduce new warnings that the compiler detects, and that as we go through our code and incrementally change it, we try and fix the ones that we encounter. We want to converge on a system that works very well. So this figure illustrates our automated testing and reporting system C-. I believe that Miriam on Friday is going to describe it very briefly with pull requests, or maybe that will be Mark. The figure is purely for illustrative purposes. Sabre does not have this many issues. I just generated some bad data so that we could have a nice slide. And then following that, whenever you write something, you should program defensively, and you should always test your assumptions. So if you're comparing two variables from Yoda, you should check that they're the same size or that they have the same number of elements. If you're reading in user input, you should always validate that it makes sense before you try and move on in your programming logic. If you're writing a multiple step program, we should always try and check to see if a step has failed before we go on to the next task. There's really no easy solution to this. You do have to program in these checks yourself. We do, however, have a policy that any new code needs to also have some external testing written for it. And that's why we do have unit tests, which is the subject of one of our talks and practicals later this week. Anyways, I hope that this talk has helped you to understand C++ a bit better. If not in practice, then at least in theory. And I hope that you can apply this to understanding JEDI, or to really whatever software you find yourself working on. There are many resources out there, and that's one of the big benefits of using a popular language. So let me just say thank you very much for your attention, and see if you have any questions.